Okay, so we're recording now. This is week 4, February 5th, 2014. And I think our primary goal for today should be to get everybody set up for success on Project 2A. All right. So we'll focus on that. We'll see how much time for other explorations we have. A few announcements. So you probably got my message that should have gone to your Loyola email about the Esteem information session. Okay, so that's Thursday at 5 at Lakeshore, Cuneo Hall 109. And Esteem is what you could call a +1 master's program, meaning you can get through it in 1 year for STEM majors, science, technology, engineering, math majors, and it focuses on technology entrepreneurship. So it's different from, say, an MBA in two main ways. One is your typical MBA program requires work experience at your typical MBA program at one of the top institutions. And also, typically, when you get an MBA, you have to put your technology hat aside, whereas this program is about the synergy between technology and business. So it's basically about this process of taking an idea and going through the process of ultimately taking it to market. So, if that's something you're interested in, check out the information session. Now there's the catch, which is the conflict with the Chicago Java User Group event. But the solution is, if you decide to attend the Chicago Java User Group event, the people from the STEAM program, above all the assistant director, Sunny Shah, he's very open to answering questions by email. You could look at the materials on your own and then follow up with email if you have any questions. So if you have a conflict, consider attending the CJOG double feature tomorrow. So this is a straight link to the event. RSVP is recommended because it's getting crowded. This is here in this building, and I don't see the room number here. It's I think it's probably one of the auditoriums on the second floor. So, geez, they might post signs. I don't know what they're doing here about that room number. I'll try to remember to let them know, so maybe they'll add the room number to this post. So anyway, it's a double feature on these two topics. So Gradle, some of you know from last semester, which the Android build system uses now, and this interface-driven design of multi-tiered web apps. So especially, if you took, for example, server-side last semester, this would probably also be a really good presentation to check out. Then next Wednesday, there is the ACM presentation on big data. And let me make sure we're recording. Yep. So even though this is not, let's say, immediately tied to the topics we're studying in this course, I feel that it's such a relevant topic for any computer scientist that we should actually go there, and end early enough to transition to this presentation. Okay. I mean, ultimately, it's optional for you to attend, but I want to make sure everybody has the option. Okay. So we'll do the usual thing, end around 6:15ish. So we'll catch a few muffins they might have left, and then attend the presentation. Okay. So that's that. Let's see, any other announcements? Basically, so I haven't posted Project 2B yet, but I'm also working on that. I know what it's going to be. So let's jump right into the material that we need to master to square up Project 2A. So I know some of you are working on it. The questions have started to come in the group, so that's good. And let's look at these basic building blocks of what are called algebraic data types. Now, here's the thing. So when you work in a language that is either purely functional, such as Haskell, or you look at a hybrid language that comes from the functional end of things and has object-oriented features added to it later, such as F#, which is a relative of Haskell. The common ancestor is basically this ML family of languages. There's also a language called Miranda up there in the ancestry. But when you come from a language like that, you can express algebraic data types very directly. We'll see this in the examples that we can study. Okay. Scala comes from the other end of the spectrum. So it's also a hybrid functional object-oriented language, but we should really say hybrid object-oriented functional in the sense that Scala you can think about as a layer on top of Java that provides functional language syntax and makes basically something that's an object-oriented language underneath that makes the object-oriented language underneath look and feel like a functional language. And on top of that, it makes it more of a pure object-oriented language, which you will see, for example, you don't have in Scala anymore this small int and big integer wrapper distinction. So that all of that is as it should be from a language design point of view. All of that is now transparent. You don't have to, as the programmer, you don't have to be aware of that anymore. So Scala is basically fundamentally object-oriented with a lot of functional syntax added to it so that it really looks and feels like a functional language. But the consequence of that is that you don't express algebraic data types as directly in Scala as you would, let's say, in Haskell, where you just write it down. You just write the data type down. So in Scala, you have to follow a certain idiom that you are already seeing in, say, the shapes project. Okay. So we'll get to this shortly. Just want to throw a few things into the room so we have the terminology. And let me tie it to the material we looked at last time. So we had option, right? And we saw, well, there's a none, and then there's a some value A, right? So this is a Scala representation of an algebraic data type that you would, if you had that mechanism, you would write like this. So you would write it kind of like this. Okay. All right, so meaning that there is a name for the concept that this type represents, and then in this case there happen to be two choices. Okay, so the vertical bar suggests an OR, and if you look at the fundamental building blocks, OR corresponds to some. Okay. whereas a logical AND, or putting multiple things together at the same time, that corresponds to product. Okay. Let me give you an example of something involving a product. Okay, so when you see the vertical bar, formally this is called a sum type, and you want to think about it intuitively as having an alternative or a choice. And in fact, for the values, so this means that an option value, you would have the choice between a none value that is part of this type, or some specific, so a sum value that wraps around some specific other kind of value, so some 7 or some string hello. And the A, okay, this is the type parameter. So the generic type parameter, that is the last item on that second line, right? And you have the same thing here. So this means you could have, for example, an option over an int base type. So, for example, sum 3 would be an instance of option of int, whereas sum hello would be an instance of option of string. Okay, so it's just like the generic Java collections that you're used to, where you can have a list of int. Well, in this case, you have to use the wrapper type, so list of integer, or list of string, or list of shape, that kind of stuff, right? So the same is the case for option, or the same is the case for these pair or other tuple types. So this means when you have more than one thing there at the same time, meaning aggregation, that is product. Okay, so aggregation, or you want to think about this as, let's say, or tupling, when you put things together as a tuple. So that means, as opposed to the choice situation where you're going to have exactly one of these alternatives in your value, here you could have, you have to have all of these pieces there. So for example, 2, 3, that would be a pair of int, whereas hello world would be a pair of string. So the same kind of stuff applies. So here we're seeing sum for alternatives. We're seeing product for aggregation. We can see arity here. So these are types with arity 1, meaning they take one type parameter, Whereas if you look at int, this is arity 0, because this is ready to use. It doesn't want a type parameter. Whereas option or list or pair, unless you give it a type parameter to say what the item type is, it's not going to be meaningful. It still wants that type parameter. Does that make sense? Then you could have another kind of pair that has arity too. You could have the kind of pair where A and B are of a different type, something like this, A comma B. So then you could have something like 3 and hello, and this would be a pair of A being int and B being string. Does that make sense? So that one, for it to work, needs an A and a B. So that is of arity 2. So it's just like for functions. Functions can have 0, 1, 2, or more arguments that before they can fire and produce their ultimate, final result, they need those arguments there. You can, in some cases, provide the arguments successively, but the function is not going to be able to give the final answer until all the arguments have been provided to it. And it's the same thing here. You have to have, if you have an arity of 1 or more, you have to provide those type arguments before that, what do you call a type constructor, will be able to work. So, quick picture here, because it's not going to show up in the video. Fair enough. All right. So, well, should have put here arity 2. It wants those 2 type arguments. Okay. Recursion. Okay. What does recursion mean in the case of a function? Any volunteers? Yes.
It represents a recurrence, like repetition.
Right, and how does that usually show up when you look at the code, at the definition of the function?
You have a condition, a base condition, and then like a recur, like so that the condition. So there should be some base condition where you should stop, and then there is a calculation or a computation in the function.
Right. So that is usually the case. So because at some point you have to terminate, so it's tied to induction basically. But in the part that doesn't terminate, what do you normally have in there that actually shows you that there is recursion? How is that manifest? Yes, exactly. What you were going to say?
I always end with a tail recursion.
Well, tail recursion is a specific form of recursion. So tail recursion doesn't happen automatically. That's if you program a function in such a way that that the very last thing it does is call itself. Then that's tail recursion. Any other comments back there? You were going to? Okay, same thing. All right. Right. So the key point is you recognize a recursive function because it somewhere calls itself. Exactly right. So meaning factorial, for example, you can say factorial if you do a case distinction like you were saying. If the argument is 0, you just give the result right away. So result is 1. If the argument is greater than 0, then you say the result is the argument times the factorial of the argument minus 1. And that's the self-call. So that's what makes this function recursive. That's right. Very, very, very true. Okay. So, and then whether or not you have that case distinction, that's really mostly about termination. Yeah, sure, it's going to be hard to have a recursive function that terminates without some kind of case distinction. Okay. Now we can apply the same idea to types. Okay? And you can say a type is recursive if it is defined in terms of itself. So if somehow the type that you're defining somehow shows up in its own definition. Does that make sense? So the same idea applied to types. Is that the case in any of these types? So really, it's just like in a recursive function, so the question boils down to, does the type you're defining, meaning what's on the left side, does it show up somewhere on the right side? And if not, then it's not a recursive type. So that's what I meant, last time when I said that option was not recursive. That's a separate thing from being able to nest types, to have sum of sum 3, which means it's an option of an option. But we'll see immediately how a recursive type is actually different. But so does that make sense? So we're not using option in its own definition, so option is not recursive. Same thing with pair. We're not using pair in its own definition. Okay? So these are not recursive. Now, let's look instead at one of our examples. So let's look at okay. Now I gotta be careful which is which here. I think this is the one. Yeah, I think this is the right one. Okay. And let me make this bigger. Okay. So again, think about what you see here as this is the Scala idiom for expressing the idea of one of these algebraic types. You'll get to a point where this is you're doing this mapping automatically. So here you see the type that you're defining is the thing at the top. So the trait shape. And don't worry about the sealed part. That just means that the pieces of it, or the different choices as part of the OR type at the top level, have to be defined along with it at the same time. So you cannot add more choices later. That's what the sealed means. So when I say trait shape, it just basically means I'm introducing a type. And then I have subtypes where they say I extend shape, and those end up as being the alternatives or variants or the choices. So this gives rise to an OR type at the top level. So in a language like Haskell, I would write it like this. Actually, we can put that here, actually, because it's valuable documentation. All right. So we would write something like data shape equals rectangle, and then I'll keep this short, or location XY shape. And now I think you're starting to see what I was trying to lead to. How is this different from, let's say, the option or pair? What's kind of a striking difference? That's right. That's exactly right. So this one has an occurrence of shape in its own definition. So it's different. This is actually defined in terms of itself. So this is a recursive type. Okay? So it's different from what we have here. So what does this mean in practice? Well, again, so the vertical bar means the shape could be either a rectangle or it could be a location. But to construct a location, so the way these case classes work in Scala, you might ask in general, so a case class, well, that means you don't need to say new when you create a value of it. And it also means that these instance variables are automatically public. If it's not a case class, if you don't say val, then they're going to be private. But you can construct basically the instance by providing the corresponding actual arguments. Whereas in a case class, those things are going to be public automatically, even though you don't say val. And you create instances basically by using an invocation with the right kinds of actual arguments of the right types. So whether you have a case class or a regular class in Scala, the default constructor, you can see what the default constructor is from whatever is in the parentheses, from the arguments in the parentheses, between the parentheses, as part of, right after the class name. Okay. Then this other stuff like extends, that's kind of like in Java, with the difference that in Scala there aren't interfaces, but there's this generalization of interfaces called traits. But traits can play the role of interfaces. A class can extend multiple traits. It's not limited to one, but there's also the idea of a superclass, and that's also based on single inheritance. So exactly one superclass and 0 or more traits in addition. Okay. So to see how we're using that constructor, we just need to look at the test fixtures. There are the examples. So to create a rectangle, you just use the constructor because it's a case class. You don't need to say new, and you provide the actual argument values, and they go into those slots. Does that make sense? It's pretty straightforward, right? So now the thing is, with the recursive one, location being defined as a product, right? Again, when we put things together, it's a product or aggregation. So an int, another int, and a shape. Whoa! So there's a chicken and egg problem if we look just at location. So it's similar to recursive functions. If we didn't have rectangle, we'd have a hard time actually building an instance. But the beauty is we have rectangle. So we can build a rectangle from nothing. So here's our rectangle. But to build a location, we can take any existing shape and then wrap that location object around it. And there we have a shape with location as the top level object or node. Does that make sense? So, in other words, this is exactly the kind of stuff you could build with a similar object-oriented representation where you have, let's say, an interface representing shape and concrete subclasses or implementations of that interface representing these variants, meaning the choices, right? So everything here is like you're used to in an object-oriented language if you were to build these kind of object-oriented tree structures. So the only thing is, with rectangle and location, we cannot build very rich shapes. So what would they look like, just with rectangle and location? What would more complex shapes look like? Meaning we could have just a rectangle, right? Then we could have a rectangle at a location. So then we could take that and have that at another location. So we can only stack more location information on top. So what is the shape of that resulting structure? Is there any branching, or is it just a straight linear thing, basically? Every time you can only basically add one level on top of, let's say, a starting point like rectangle. So you can never introduce any branching, and you will have only linear structures as a result with just location and rectangle. That's right. So that's why I don't want to say yet what design pattern it is. But as part of this exercise, you're going to introduce a group construct. And that one says, okay, I can have a rectangle and another rectangle, and then I can say, okay, these two form a group, and that group behaves as if it were just a single shape. So there you get branching, and then you can have arbitrarily complex and rich trees of shapes. So in terms of design patterns, what design pattern does this group node represent? Exactly. That's right. It's a composite design pattern. And location? Exactly. So typically, when you have the relationship where the node that you're looking at, or class that represents a node in the kinds of structures you're building, when it's an implementation of the general overarching concept and has one child, but adds a little bit of information to that child, so just like location, that's a decorator. And when it has multiple children, so depending on your domain model, 0 or more, or 1 or more, or exactly 2, or exactly 3. So that would be a composite, because then a composite node is then substitutable for any other nodes in this general structure, and that allows the creation of arbitrary hierarchies with branches. So you have arbitrarily rich hierarchies here. Does that make sense? Excellent. So the key point is, though, that both location and the other one that you will add, which is group, have recursion, and basically the recursion shows up if you were to draw a class diagram. So that's what I was just describing in words. Let's say you have shape, then you have location, and group. So these are both subtypes or children of shape in the class hierarchy. And location has a shape as a child. So that's the recursion. And then group has multiple shapes as children. So that's, again, the recursion. So meaning, when you have that, the reason it's not a cycle in the inheritance hierarchy is that it's a hazard as opposed to a subtype relationship. You cannot have cycles in the subtype relationship. The language won't let you, but you can have these references or hazard relationships. The product kind of relationships where parts of that product can be the type itself. And that allows you to stack things or even build trees. So one will allow you to stack. Multiple ones will allow you even to have nonlinear structures as a result. Okay. And that's summarized here. So option is non-recursive, so is pair, or enum types. You can think about almost all types as algebraic data types. You can think about int as an OR with these various possible int values enumerated from the minimum int value up to the max int value. So these are a lot of values to enumerate. That's why it's not usually presented like this, and you don't want to think about it like this. But in principle, you could reconcile it with this algebraic data type view. Okay. With Boolean, it's very easy. Boolean is like option, but the sum doesn't have a value attached to it. So you could think about it in that way, right? So those are all non-recursive. Finite enumerations, option. There's also a thing called either, which is like option where the none also has a value. So there's a left with a value or a right with a value. Very similar to option. It makes sense, the left could represent an error value with more information, and the right could represent a successful result value with a value attached. Then you have linear recursive types, and then you have nonlinear ones such as the general tree type or these kinds of custom tree types like our shapes type. Now, what about this sublinear stuff? That's kind of weird, but we'll see an example shortly. And what about how is list a recursive type? Does that make any sense? How is that yes?
Actually, in list, if you program in list, so it's very obvious because a list has two parts: the first and the right.
Exactly.
So you recursing that.
That's right. It's just. Exactly. So we're about to see some examples like that. It's just that when we come from, for example, Java, we just think about it as just a linear container, and it's not obvious to us that there's any kind of recursive structure. But the way you could define list is like this. Okay. So this is not obvious yet, but I was just kind of describing, what if you had only, well, you do need a base case, so rectangle is a base case because that doesn't have any kind of relationship back with shape other than just being a subtype, right? So this has a relationship back. Okay, so if we had just rectangle and location, anything that we build is like a list. And what kind of stuff is in the list? Well, the X's and the Y's. Does that make sense? So, for example, you could think about this one as a list with the rectangle at the end and then the location. Or I could make another one. Okay. So I could have, let's say, another set of values, 85, 20. Okay. See how now it kind of extends toward the front? Or this way from your perspective, right? So you could kind of build a list where you start from the end and then you add more stuff at the front. So this is how lists get built in Lisp. But when we work with lists, we think about them not in this kind of piecemeal fashion, like one item at a time. Here, it looks kind of like a one item at a time thing. And that's too granular. So it's okay. We want to think about lists as aggregates. That's a good way of looking at it. But it helps for us to understand how to write functionality on these kinds of types, how the list methods and functions are actually implemented. Anyway, so we'll see if we have time to come back to that. I want to basically, let's see, go through an example I rigged up. So there, you should be seeing a project called MISC Exploration Scala. So let me pull that up on Bitbucket. This one here, okay. This is what we're looking at here, and this includes some of the examples we had last time. But the one that is intended to prepare us for Project 2A is this org chart one, okay? And what we have is, again, a kind of algebraic definition here. And this is Haskell syntax. And again, as long as we can kind of read these Haskell definitions, that's all we need for here. You know, at some later point, you might want to play around with Haskell a little bit. But and you might ask, why aren't we doing Haskell in this course? Well, that's a good question. You know, we could have all of these discussions with examples and projects in Haskell, but there are certain other advantages that Scala has. So for example, it runs on the Java virtual machine, and there's kind of a better ecosystem as part of this broader Java community and the interoperability. But now, okay, I got to say one more thing that applies retroactive. Well, you don't have to worry about it retroactively. But going forward, I should have said this sooner, but going forward, please keep this in mind. Don't try to interoperate with stuff from Java unless you have to. Meaning, when you write Scala code from scratch, you don't have those liabilities. So don't use stuff like the Java lang integer or the Java collections. Interoperability is provided, but that's really for, let's say, if you for some reason have to use a legacy Java library. Okay, but you don't have to do this here. You can keep things much simpler by using the Scala collections. The Scala API documentation has this nice incremental search, right? As some of you have said, it's easier to use. It also flattens the inherited methods and gives you one flat list. It's much easier to see what there is. So, take advantage of the fact that those things are provided in a nicer way within Scala itself. Okay. So if you're finding yourself trying to interoperate with legacy Java classes, you should step back and say, am I going into a dead end here? Anyway, so coming back here, here's the definition. So there's the vertical bar for the OR. So there's a choice to define an org chart. What is an org chart about? It represents hierarchy in an organization. So what kind of data structure is it if we look at our little classification here? In which of these four categories would you put the org chart? Nonlinear, exactly. This is designed to represent an actual hierarchy with possible branches, different levels, etc. Arbitrary number of levels, it's not limited. That's why you have to have these kinds of relationships along with this one, okay? So within itself, and that's the essence of these kinds of recursive types, you can build structures without a preset number of levels, right? So you could have many levels, or you could add more levels. So any instance is going to be finite, but there's no preset. It's like no preset spending limit. There's no preset limit to the depth of the hierarchy that you can build. And the same thing with a list. There is no preset limit. Lists can have only 28 items or so. So they can be arbitrarily long, but lists are are inherently finite. Then you might ask, are there infinite structures? Is there a way to define infinite structures? And even though that might be a little hard to grasp, but yes, we could define infinite structures as well. It's going to be hard to print them, for example, but you can print a piece of them. So, for example, if you think about the list of all positive numbers starting with 1, okay? If you try to print that, you'll never end. But if you say, okay, let's print the first 100, that you can do, right? So you can have those structures in your program as long as you always, let's say, or in certain situations, you work on a finite piece of them. Then you can have meaningful computations involving infinite structures. So that's another topic we'll explore. Okay, very good. So we got this nonlinear, and how do we define this? Well, very simple org chart will say there could be persons. Those are the base cases. That's the non-recursive base case. Or we could have an OU, meaning organizational unit, like a division in the organization, and that would have a name, and it would have 0 or more children. Okay. So how could an OU have 0 children? Well, if it just gets created, maybe no one has been assigned to that unit yet. That's a possibility. So the children could be just an empty list. That's no problem. So then that maps directly, almost mechanically, to Scala like this. So we have our sealed trait corresponding to the type we're defining. Then we have for each part of the sum, for each variant, we have a case class that extends. That's important, right? It extends the type we're defining. So the extend gives us these arrows in this two level type hierarchy. And then so we have P, which has a name, and we have OU, which has a name and a list of children. Okay. And so in these worksheets, by the way, so we can just embed these ordinary Scala assertions, which are like Java assertions. So it's like, when we do this exploratory stuff, it's kind of integrating the test-driven style a little bit right into that. So we write a little bit of code, we test a little bit, and when we run it, we'll see the exceptions. I think we saw that. Okay. Any questions so far? We can now define instances. So we can define a node for George. Okay. And so we have one, that's an org chart. That's just George. Okay. But then we can have more interesting org charts by building these hierarchies. So how about the computer science department? That would have that name, CS, and then a list of children, and those could be actual persons in this unit. Okay. So here we can bottom up successively build hierarchies. Here's the math department. The College of Arts and Sciences would be also an org unit, and its children are immediate children. Let's say the dean's executive secretary, and then this is where you can have these multiple levels, right? So an OU is a node, so that's why I can mix leaves, meaning the base cases, leaves of the tree, with subtrees, non-leaf subtrees, such as these other OUs, right? So you've seen all of this kind of stuff in object-oriented representations, and you can see that it's a little easier here with these case classes. A class becomes a one-liner here as opposed to, each class being, 10 or 15 lines or whatever. And then you can create these things very simply. In Java, you could write this code also, but you'd have to have a new for every node. That's a little saving here. That makes it a little more concise. Anyway, so then we could say, okay, Loyola is, the list of as children, their college, and then other academic units like the School of Business, etc. Any questions so far? Makes sense, right? Yes?
Is that more object-oriented or functional?
This is really something that's in common. The style is a little bit hybrid in the sense that instead of writing that data type as a sum and product type, right, as a one line defining the recursive data type with all its terms and each term having maybe a product nature and being recursive and so on. Instead, we have to use this idiom, which starts with the overarching trait, and then one level below the different variants, which are the concrete kinds of nodes that we can have in these structures. Okay, so that is hybrid object-oriented. I mean, that's more object-oriented. The fact that we have subtyping and so on. But it's an idiom that we use commonly to express the line in the comment in a language like Scala. Okay, but then this kind of stuff where we actually create instances, this would look very, very similar in a pure functional language or in an object-oriented language. So in a ordinary object-oriented language, all you would add would be the new keyword for each node. So you'd have a lot of news in there, but everything else is the same. Other questions so far? Okay. So now we can define recursive functions on these things. So now maybe this is a little bit of a déjà vu of your CS2 course, like the 271 course, where you might have done these kinds of things where you might have defined functions outside of the classes. I'm not sure, depending on the language and the approach, right? Okay, so how do we count the number of nodes in an org chart? And this is exactly, applying something that you were saying earlier about processing lists, like thinking about a list as the head and then the tail. Very similar. So here, we have to think about a base case, and then we have to think about a recursive case. And we know what the possible cases are. They are our case classes, the different variants of the algebraic data type. So how do we define the size conceptually? Well, we say every person in the org chart adds one to the size of the whole thing. Does that make sense? So OUs don't add anything, don't contribute to the size. But if you look at the whole tree, and you think about every person as an apple, you shake the tree and then you count the number of apples that fall. Okay, so those are the leaves in this case. Okay, so how do you do this? Well, when you're invoking the size function, the argument is a node, because it could be an arbitrary org chart, and node represents that. Okay, and then you have to make a case distinction. So it's the usual thing, just like the factorial, where the case distinction is based on the actual numeric value of the argument. But here it's based more structurally. So this is a structural recursion. Okay, so you look at O, and you're saying, what's the size of O? It depends. You have to make the case distinction. If it's a P, meaning that's a person, and we said, well, every person, whenever we see a person, we know the answer, so the answer is 1. So in that case, we just return the 1. If it's an OU, however, then we have to say, we can't give a straight answer immediately. We have to say, well, it depends on the sizes of our children. So it's 0 for the OU plus for each child the size of that child, and then adding up those sizes. Does that make sense? And that is the recursion. So the recursion is here. And this is you will see that this is a common pattern that's emerging. And there is also a fancy Greek word for this type of operation, which I won't introduce yet. But what we're doing here is, the map basically says, for each child, get the size of that child. Map means apply a function, so little map, meaning map method. So take whatever structure you have, apply the function argument to each item contained in that structure. So the children, what are the children? The children are a list of nodes, okay? So we'll apply the size method to each of those children. Then what do we get out of that? We get a list of size values, right? Where before we had the list of org charts that are the children of the current node. Then we say, well, get the size of each of those. And now we have a list of numbers from the list of org charts that are the children, right? So now we have the sizes of the children. And then my own size is just adding up those sizes. So sum. And we're done, yes.
So you're passing the function size. You don't need to give an argument to size because it's you're already getting one. Is that?
Yes, exactly. I'm glad you're drilling a little bit into this issue. That's right. So again, maybe pedagogically this is not the best way to write it. So maybe we should write it like this. So node, and then size of that node. Okay. I can write it like this. So meaning, now it's clear that what we're passing to map is a function that wants a node and then applies the size function to that node. So this is much more obvious now, right? So the map applies this function to each child. So we get back a structure like the original children structure, but with the results of the size function. Okay. And now the shorthands are, you can go like this, with the underscore, or you can just get rid of it, so that's where that comes from. But yeah, thanks for the opportunity to point that out. That's right. So that's the recursive call. And then, so the very common pattern is to invoke the method that we're defining or function recursively on the children or neighbors. And then we have a resulting structure that has the results for each child or neighbor of applying that function. And then we have to combine that structure with the results in some meaningful way. So once you see the depth, I think you will start seeing the pattern here. Anyway, so let's run this guy here. And you can see how the assertions work. If it doesn't complain, it means it succeeded. You won't see anything. So see how the George, that succeeded, and then there's some failures because the triple question mark means method not implemented. That's a nice shorthand for saying that, well, you still got to do that method. But it's much better than returning a dummy value because if you try to invoke it, you get an exception. So you know that you still have to do it. But see, so those size tests worked. So if I get rid of the output, see here, so size of P is 1. That worked. Size of the CS department, that had 3 persons, that worked. And then size of LUC, that just counted all the persons in there, and that worked as well. That's those 2, and then 3, and 3 more. So regardless of the depth, this worked. And it'll just, whenever it's presented with a child, it'll reapply this case distinction, and then it'll ultimately traverse the entire tree. So it is equivalent to a depth-first tree traversal. Okay. Other questions? So let's take a look at depth. So the next challenge is to calculate the depth of the org chart, because that's always an important thing, you know, when the consultants come in and say, how can this organization be more efficient? Well, you got to make it a little flatter. And I'm not sure how many of you follow Dilbert, but there was this one Dilbert where the consultants come in and try to understand the organizational structure. And then they have this huge org chart, you know, very hierarchical. And then Dilbert's position is somewhere below the consultant's foot or something. So that's a non-flat organization, right? So the depth is basically when you have a tree, it's the length or height of the tree. It doesn't matter, depth or height. Height's probably more official as a term, you know, but I'm just calling it depth here. So it's the length of the longest path from the root to a leaf. Right, that's how it's defined in your data structures class. How do we compute that here, recursively? And now I got to do that little magic, you know, close and reopen. We got to report that bug. Anyway, okay. What's the depth of a person? That's just a tree consisting of one leaf. Well, we're defining that to be 1. Okay. Now, what's the depth of a tree in general? You know, you have an org unit, and you have multiple subtrees. What's the depth of that? How would you express that? Suppose you have 3 children, and the depths are 3, 7, and 4. What's then the depth of that OU? Yep. 7, and maybe one more for that node, right? So how did you determine that it was 7? Right, exactly. That's the key thing here. So the pattern, you know, you can, let's do this together. So you can almost copy this line, right? You copy this. Okay, but we said, okay, if we have multiple answers for the children, we don't want to add them up, but instead we want to pick the largest, right? So, you know, in a nice collection API, there is a way to get the max from a list or other similar structure. So, you know, it helps to know the API. Of course, you could have done a little linear search to find the max. Yeah, but that's what this does. It's the only thing you can do. There is no magic for finding a max. It's an exhaustive search. That's fine. Okay. And now, depth of person should be 1, and then of the whole university should be 4. So we can rerun the worksheet, and we can see if these things now pass. So stuff's happening. I think it's a little faster now that I took the Scala Z stuff out of these. So, yeah, so either up. Ooh, what's going on here? That's really bad. And thank you. That's a good catch. Okay. See, I did too much copy and paste. So thank you very much. So we'll change this to depth, and now we'll rerun it. See, that's, if I could say, oh, I did it on purpose to see if you're on guard, but I really didn't. It's okay. So now it either failed to terminate, or there's still some problem. What's going on? Well, here's what we'll do. We'll have to understand quickly what it thinks it's doing.
You forgot to do 1+.
Okay. Excellent. Okay. Excellent. Thank you. Right. So I forgot to add one more for the actual node we're looking at. Great progress. See, that's the beauty of this, of thinking about what you're expecting, of articulating what you're expecting as a little assertion. It's very simple yet extremely effective. Okay, looks like there's room for such a long stack trace, so I think we're good. Yes. Okay, with your participation. See, that's what I had hoped for. Okay, so now what is the pattern that we're seeing here? And oh man, I gotta do the close open again and resize. Okay. All right. So see, the pattern that's emerging is in the interior node recursive case, recursively apply the method we're in the process of defining to each child. The map does that, and then somehow combine the partial results in the appropriate way and do other stuff with it, like in this case we had to add a 1. But that's kind of the pattern that's emerging. And this will, because map applies this function recursively, the recursive case will kind of propagate through until we reach the base cases, the leaves in the tree. So this is kind of the underlying pattern. Okay, any questions, comments? Does this make sense? Is everybody comfortable with this? And does everybody see how this is basically what we're doing for Project 2A? We're just, the challenging thing in Project 2A, but you have to kind of follow those links to get to, either, or I mean, dig up your project from, was it Project 3 from last semester, the Android version of the shapes. So the bounding box algorithm, you can get it from there, or there's that some sample midterm from an earlier course I taught, and that has that as well. I mean, the thing works like this. The bounding box, you start with an empty bounding box, meaning it's kind of like this, and then any actual bounding box will set it straight and take over, and then you have other shapes, and then you expand. So meaning this initial bounding box is an infinitely negatively sized bounding box. Basically where the, let's see, normally you have the smaller x here and the larger x here, and in this case the large x would be negative max value, and the minimum, the smaller one would be plus max value, and then that means it's like starting with the smallest possible bounding box in such a way that any actual bounding box, let's say from a rectangle that sits here, will then take over, and then you find a rectangle there, then you'll grow the bounding box accordingly, So bounding box is kind of, you have the shapes and then you shrink wrap a rectangle around it. Any questions about those algorithmic aspects of the shapes project? Yes.
Concerning math, is that the same math that can be written without a dot?
Yes. Okay. So what about this dot business? Okay. So I've probably not been consistent with this, and the Scala style guide says that you should omit the dots, and you can also omit the parentheses when it's this kind of thing where you're starting with something, and then it's an alternation between method, argument. You have a chain of invocations of one argument methods. And then for the last thing, you can also omit it. But then you get that feature warning, so the whole thing is a little tricky, and there are just there may be too many ways to write something. So you can write this. So the sum is kind of a postfix method without argument, and we can omit the parentheses. So you want to do that when the method is side effect free. So for example, when you say print ln, that has a side effect of actually altering the output. So there you should put the empty pair of parentheses in println. But sum is side effect free. It doesn't change the argument or the receiver on which you're invoking it. So there it's actually considered good style to omit the parentheses. Now, there are other intricacies. For example, if you have another expression on the next line, then it might get confused. So if you run into trouble, you could just do it this way. Okay. So that's one possibility. Or you could put parentheses around it like this. So just try some of those things, but you can always fall back to the standard object-oriented syntax, which means the dots and the parentheses for the arguments. And then you might sometimes see things like the curly braces, and then typically when curly braces are used, you use more space around it. That's when you want to make a method invocation look kind of like a control structure. So you can, in Scala, when there's just one argument, you can use curly braces instead of round parentheses. So the examples, I'm trying to be consistent, but I might not always achieve that. And that's why it's a good thing you asked. But for your own code, if you have any trouble, you can always just fall back to the default object-oriented syntax, and you should be fine, like in this case. Okay, any other questions? So I want to show, let's see, we have a few minutes. So we have two presentations today. The presenters prepared and ready to present. So we'll transition in maybe, let me see, in maybe about 5 to 10 minutes we'll start the transition. I want to show a couple of examples here. This is actually a good connection between this conversation about recursive types and how, just as Nasser mentioned, how lists can be viewed as recursive types. And the way you would define a list type, it's very similar to what we have here, but you would say something like data list, or actually, let's write it here. Oh, is it there? No, that's just code folding. Okay, so data list of A, so A being the item type is, I'm doing a little bit of hybrid syntax. It's either the empty list, which is usually called nil, or it's now you could either call it cons, meaning you're constructing a list from an item and an existing list, or you could express the cons as an operator. And you could do it like this. So an item of type A cons with a list of A. So that's now consistent with the syntax we have here. And the beauty is these algebraic data types, when you write them down or when you look at the case classes in the Scala style of expressing these, they have their counterpart when you do pattern matching. So in other words, you can match for those alternatives in a match case expression. And here is, and this ties to our little test we had, right? There was a thing that you might have recognized as a reverse. How do I reverse a list? And what we're doing here is the same kind of thing we're doing here, where we write behavior or functionality in terms of a case distinction among the different variants we have. And for list, we have the two variants, either empty or non-empty, where a non-empty list gets built by taking an item and putting it in front of an existing list using this const or double colon operator. And the list, if you have this kind of list, let's say, or actually let me show that here. Let's see if that works. So if we run this little thing here, it should be the same as just writing down the list of 1, 2, and 3. See? So that first thing, it says, okay, that's, we could write it as an assertion that is equal to list 1, 2, 3. Okay. All right. So that gives you the idea of the role of the const operator, and this is the connection, right? Normally coming from a world where we think of these linear collections as just an aggregate, kind of an aggregate that we index into or look at the head or the tail or whatever, do stuff with, iterate over. We think about the right side here of this assertion. But to understand really how to implement functionality, kind of basic functionality on these kinds of structures, it helps to take this left side view where we think about it as an algebraic data type. So the way we can do a reverse, again, very simply with a case distinction, how do we reverse a list? Well, if it's empty, it's easy, right? It's still the empty list, it's its own reverse. And what about a non-empty list? So in some way, we want to, let's say we look at the list at the top, we want to put that 1 at the end. Does that make sense? In the first step. And then reverse whatever is left. So the pattern matching works like this. The pattern matching corresponds to this thing. Does that make sense? That's not how it's implemented in Scala. In Scala, it's called const. But there's this double colon operator provided as extra syntax. But that's really kind of an implementation detail. Conceptually, it's there, and it's there in such a way that the pattern matching works. So what we do here is we are breaking up the incoming list, and you might want to say, hey, where's the argument? Well, the argument here is anonymous. Really, I'm just saying here, reverse is something that takes a list of item type A and returns a list of item type A. And the argument is anonymous, so with the case distinction here, it's a kind of terse or syntax. Otherwise, I would have to say list L, and then L match, and then it would still look the same. So that's just redundant. That's why it's actually nicer to write it like this. So the way you can think about it is, okay, is the incoming list a nil? Okay, then my result is nil. Or is the incoming list of the form head, meaning one item at the front, put together with or const with some remaining list, which might or might not be empty. And that's the T, the tail. And I can say, oh, no problem. I'll reverse the tail recursively, and then I'll stick the thing that was at the head before at the end. Okay, and that's what we're seeing here. So this means add an item at the end. Does that make sense? And the way we had it in on the test was like this, right? So we could write almost anything like that as a fold. Okay. And, that works the same. How does that work? Well, the fold, when we apply the fold you want to think about the fold as in the Scala for the intrigue talk. I like to write the fold as a control structure, although it produces a value. But I like to use these curly braces to write it as a control structure, meaning when I do the fold on this list, we start out with, and if the list is empty, that's what we end up with, whatever is here. So that's kind of the initialization. And we start out with an empty list, and then we get fed in the fold. We get fed one item at a time as this X. And at every step, as we work through that list, so we get each X value here, and we also get whatever result has been built so far as the Y's. That's the first argument of this function here for every step. And then we can say, oh, if we do that, then we just take the X and we put the X at the beginning of the result. And it works because it's a fold left, so we get the arguments from left to right. So at the end, we have the rightmost argument, and it gets put at the front. So it's kind of in opposite order as the direct recursive one. Yeah.
Is the double colon different than plus colon?
Yes. It's the opposite in the following sense. Double colon means item prepended to an existing list. So when you have a list here, Y's, and this item becomes the new head of that list. Whereas here with the colon plus, you take a list and then the item you're adding gets stuck at the end.
Oh, I was talking about on the test how you had plus and then colon. Is that the same as opposed to?
Oh, that is, I think, the same. Okay, thank you. Sorry, I was. So we had plus colon like this, right? So let's run it. This, I think, is the same, because everything on the test is certified to work. Let's see. Yep. Good point. Okay. So it's probably still a little unfamiliar to think about lists in these recursive ways, but it'll become more familiar as we're looking at these things, and we're going to at some point consider list as just one type of algebraic data types, just a very common type that we're used to thinking of as an aggregate type. Okay, any questions? So we have 2 talks lined up. Let me pull up the schedule. And so it's wall clock is about 3 minutes ahead. So we can have about 3 or 4 minutes of transition time. We'll start the first talk at 6:25, and then we'll transition to the second talk at 6:35, and we'll be able to end on time. So I have here talks on C++ and C#. Okay, so you're doing C++? Okay, great. And who's doing C#? Who's doing C#? Okay, well, why don't you go ahead? So here's and then I will figure out who's on the line for C#. Maybe something got messed up. Who knows? In that case, we're